Great. So I think we've got a few more people coming in. Um, but in the interest of time, I think we'll kick off from there. I think people, yeah, trickle in as we've just got to sort of midday. Firstly, yeah, just a big welcome to everyone for coming along to this, the first of the REWIRE webinar series that we're running. Just to introduce myself, I'm Alex Oliver. I'm the partnerships lead for the REWIRE Innovation and Knowledge Centre. And yeah, so we've got our first webinar in the series, which is looking at test and measurement standards for semiconductors and looking at that with a sort of power semiconductor wide bandgap lens as well. We've got two speakers today. So we've got Dr. Seb Wood from MPL and Dr. Vish Shah from the University of Warwick, and is also one of the REWIRE academics on the team. I'm just going to sort of introduce them briefly, and then I'll hand over to them to crack on with their slides. Sorry, this bit's going to be very much sort of reading off a script. So yeah, Dr. Seb Wood is the principal research scientist at the National Physical Laboratory. He joined NPL in 2015 following undergraduate and doctoral studies at Imperial College London. And in his role at NPL, Seb has developed a unique facility for nanometrology of emerging electronics across multiple measurement modes, which has been applied to different material systems, including hybrid perovskites, nanostructured semiconductors, 2D materials, and compound semiconductors for a wide variety of device applications. Seb is a member of the Institute of Physics, a chartered physicist, and contributes to British and international standardization committees. He is currently the chair of the National Standards Committee, BSI EPL/47 on semiconductors, which I'm sure he'll talk a little bit more about later. He's a member of the BSI CII 60 surface chemical analysis and a national expert on the corresponding international IEC and ISO committees. He has also led multiple research projects with individual UK companies, as well as coordinated international collaborative research projects, including on wide bandgap power electronics. Secondly, Dr. Vish Shah is an associate professor at the University of Warwick and is part of the REWIRE Innovation and Knowledge Centre's academic team. He joined the School of Engineering at Warwick in 2017 as part of the Power Electronics Applications and Technology in Energy Research, or PETA group, which is a world-class centre for research into power electronics, power semiconductor devices, and applications in power systems. He has been working in the ultra-wide bandgap materials research activity in space, and his research interests are driven by the application-led materials development of these kinds of materials. He has over 15 years experience developing semiconductor materials and technologies for numerous application areas, including in power electronics, quantum tech, photovoltaics, and others. I also forgot to mention at the start, so before I hand over to the speakers for today, if you do have any questions, feel free to pop them into the chat or the Q&A function. I'll be keeping an eye on those as we go through. So yeah, feel free to do that. And with that, I will hand over to Seb to start presenting.
Brilliant. Thanks for the intro, Alex. Let me just pop up my slides. Have I got it up? Great. All right.
Yeah. Okay.
Thanks, Alex. All right. Thanks for joining, folks. It's great to speak to you today. And yeah, as Alex has mentioned, the topic is standards for emerging semiconductor technologies, and specifically the focus is on measurement and test standards. I appreciate that not everybody thinks standards are as exciting as I do, but what I will seek to convince you of is that they're really, really very important. And I think there's some excitement to be had as well. So I'm going to explain what we mean by standards, specifically measurement test standards, why they matter, and talk a little bit about how they apply particularly to semiconductors. But we'll hand over really to Vish, who will talk more about the specific case of wide bandgap power electronics. But first, I have an obligatory slide on NPL. So you may or may not know NPL. We are the National Physical Laboratory. We're the UK's national lab. We're owned by the government. There's a photo of our lovely building in Teddington, just outside London. And there's about 1,000 of us there on site. We work with thousands of companies, dozens of universities around the UK, as well as internationally, providing measurement science. So broadly, we have three roles. Firstly, we are the highest point of reference in measurement for the UK. So if what matters to you is really accurate measurements, then that's what we do. But we also engage particularly with national challenges. So where a particular national challenge has a measurement element, then we have a role in that as a national lab. And we also have the international focus, so representing the UK on metrology and standards committees and in the broader leadership picture for emerging technologies. Okay, so broadly, all of this is what we understand by the word metrology, not to be confused with meteorology. Metrology is the science of measurement. So it's about how we define our units, the SI system, but also about how we realize them. So it's all well and good to define what a second is in terms of transitions of an atom, but to actually make that useful, you have to realize it. And then the bit at the end, which is really my focus, is about how you can traceably link practical measurements that you can do in a lab or in an industrial setting to the SI system. This is my favorite quote. Well, it's my very favorite. It's a top quote from Lord Kelvin, who said, if you can't measure something, if you can't put numbers to it, then basically you're not really doing science. And of course, that's right, isn't it? And so metrology is foundational to all of science, but also to trade and industry more widely. So that's the broad picture. I spoke earlier about our role in national challenges, and you may well be familiar with these. This is the 5 critical emerging technologies that's been identified by UK government, and you can see semiconductors is one of those 5. Arguably, it's foundational to at least 3 of the others. The exact names have been tweaked a little bit, but these are basically still recognised as priorities. And the UK is not the only government to recognise that. Basically, all the economically active countries have recognised the same priorities, and what's ensued is a race for standardization. So here's some documents, examples from the US and from Japan, which particularly highlight the recognition that it's through technology standards that new markets, new technologies are going to be defined, and so they have this pivotal role. And it's not just other countries. The UK has come to the same conclusion. So this report came out a couple of years ago and highlights specifically that the UK needs to work to ensure that global technology standards are shaped by the UK and other like-minded nations. Okay, I've used the word standards quite a few times already, but haven't actually defined it yet. So here we go. This is the way I understand standards. It simply means an agreed way of doing things. So there are lots and lots of different types of standards that we can think of. Some of these things might be what you immediately thought of, like ISO, IEC standards, but also there's much less formalized things here. So for example, a good practice guide or industry best practices, which are disseminated by NPL or by other institutions. But even in here, so research standards, this is basically an academic effort to work out what the best practices are in doing particular measurements and to build consensus around that. That's essentially a standard. There are also physical standards. So there's one picture there of a standard kilogram. That is another thing that you can call a standard, but it's anywhere that people have agreed between themselves how they're going to do something or how they're going to define something. So that's my understanding of standards. It's not just ISO and IEC, it's really broadly understood. Okay, but what's the point of standards? So you'll find a lot of literature on standards if you really want to discover it. But this is the way that I understand it. Broadly, there are 3 things that standards are doing, all of which are to do with facilitating trade and uptake of technologies. So for low TRL technologies, so TRL kind of 1 to 3, which is probably where this community is focused, but they're not exclusively. The role of standards is around making sure you've got clarity in your research. So terminology, what do the words mean? How do we define the basic the basic words and definitions that we're going to use in our research? And then measurement standards is about how you measure a thing. So once you've defined some parameter, some quantity, you then need to work out how you're going to measure it. And For example, developing best practices for research would be something that fits in here. And this speaks directly to the reproducibility crisis that we've heard quite a lot about in recent years, where actually you can have researchers in different labs, but their results are not directly comparable or they can't be reproduced. And this essentially arises from failures of standardization. When you get to mid-TRL, kind of like 4 to 6, it's more about how you get a technology to something that can be commercialized. So here you're interested in performance metrics. So what is the performance of this new technology? How do you standardize those tests so that you can compare one thing with another and work out which is the best? That's important for actually marketing a technology because it defines the route to market, but also for investability. So when you get investment in a technology, you often have to set technical milestones for the progress you're going to make, and those essentially require you to have standardized figures of merit that you can appeal to. And then at high TRLs, we're more interested in things like interoperability and reliability, or maybe things like how you'll manufacture the product. And this is about ensuring that your supply chains are resilient, that they're efficient. And there's also a technology governance part to this. So where legislation gets involved and wants to define how you're going to use technologies, then that's, again, another kind of standard. All of this applies to standards in general, but what about semiconductors specifically? Well, you may know that the semiconductor industry is extremely highly standardized. So if we're talking really about the silicon industry, but there are literally thousands of documentary standards and unwritten standards that define the whole semiconductor industry. And there are some logos here of some of the publishers, the standards development organizations that are involved in that process. There's thousands of committee members involved. I've highlighted 3 of the big ones, so JEDEC and SEMI, also this IEC technical committee. But it's worth pointing out that many standards are never published. So quite often you will have some kind of specification for a product or something that you do within a company or within a particular supply chain that you would actually find quite commercially sensitive and you wouldn't actually share it at all. But it is still essentially a standard. Okay, so I've basically told you there's loads and loads of standards and it represents everything that you can imagine. But we can break it down a little bit to bring some order to the chaos. And I broadly think there are 3 types of standards and they map onto those roles that I spoke about earlier. And they build a pyramid. A pyramid is nice. You have to start at the bottom to make a good pyramid. And right at the bottom, you have measurement standards. So this is where national labs like NPL and academia are really leading the way. So at this point, it's for emerging technologies that are pre-competitive in nature, where what you need is to have clarity around measurements and basic terminology in order to enable you to innovate and to work towards commercializing a product. And this is sort of basic research, feasibility research, maps onto low TRLs. It's about building up knowledge. And to be honest, there's not a lot of money to be made in doing this. It's infrastructural in nature. Once you have that in place, you can start to work towards product standards. So the technology is clear and now you're trying to make a thing that you can sell. And this would typically be led by industry or by markets, because at this point you're trying to commercialize something. And it's all about getting it into the hands of customers. So prototype development might fit into here, but it really feeds into more mature technologies. And that gets you to this last element, which is regulatory standards. So this is something that governments would lead on because it's essentially a legislatory issue. And this is for controlling the end use of the market. So you're not defining the technology at this point, you're prescribing how it's going to be used. And this is something that government leads, but obviously industries are very engaged here as well because it essentially controls where they can and can't sell their products. Okay, so in the case of semiconductors, the way to think of it is that this pyramid basically already exists, at least for silicon technology. So the challenge is for innovators how they can engage with this existing body of standards. And the way it works is that really you're adding on to the side at each level. So if you want to bring a new semiconductor technology into this existing landscape, then at the bottom you need to have the basic metrological foundation. So if you've got a new material, the measurements that you need might be different, or certainly the definitions can be. And then to build on that, again, how you measure and test it, working towards into the product space, so how you're going to specify and manufacture this new technology, and then reliability, qualification, and then, of course, there may or may not be regulatory issues. It depends what the end use is, but you can't really regulate it until you've done the lower lying parts, because your regulatory legislation won't make sense without the foundation of standards. So to bring this to life a little bit, I've got an example. So this is particularly looking at standards that have recently been published, or some are still in development, that relate to the adoption of silicon carbide for automotive power electronics. So the very bottom layer is the really basic foundational stuff, which is sort of the SI system of units. And you can see in the second layer here, or the second orange box, where there's some ISO and IEC standards. And I think Vish will speak about this more, but these are quite basic measurements that you might need to do. So if you're doing trench etch, you need to understand the critical dimensions of that, or you need to define your defects and how you're going to inspect and label them. And then as you start to make products, this is where JEDEC and SEMI and AEC get involved, and they produce standards on reliability testing for silicon carbide power electronics, how you understand the failure methods. And then there's a SEMI standard there, which is about how you specify the wafer. So if you want to have, if you want to integrate a supply chain that you can buy your wafers from multiple places, then you need to standardize the specifications of that wafer. And then right at the top is the regulatory issues. Automotive is a regulated industry because it's safety critical, and these silicon carbide MOSFETs are being used in the powertrain. So this all has to fit into the regulatory framework, and there's this IATF certification process, which is now being used, or is now able to adopt silicon carbide. Okay, so just to share a couple of things about how standards actually get made. This is a diagram that one of my colleagues drew some while ago about the full pathway from the beginning to the end of standardization. A lot of the focus tends to be on that last bit, where these standards development organizations get involved and essentially are just building consensus and publishing the standard. But it's already essentially been created by then. So before you get to publishing a documentary standard, you need to have had a discovery phase. So whatever your measurement or test or material is, there's a body of basic research that needed to have been done. And this is where academia or national labs or sometimes industry is prepared to reach this far down the TRLs. And then you build on that with this middle bit, which is, I've called it here, pre-standardization research. So it's the body of research that's needed to take your basic knowledge and make it suitable for publication as a standard. So some of this is very kind of nuts and boltsy type things about how you calibrate correctly, making sure that your methods are reproducible. Often you would do something called an inter-laboratory comparison. So if you have a method that you want to standardize, you would write it down and you would find labs in multiple countries or different settings and get them all to do the same measurement on the same sample. And if your standard is any good, then they should all get consistent results. If they don't, you have to rethink and start again. But all of that, quite a slow process, but it's about building consensus and the body of evidence that's needed for you to take your proposed standard through to a standards committee. So obviously, if you want to get to the end of that diagram, you need to start at the beginning. And so a piece of work that we've undertaken at NPL over the last couple of years has been to do stakeholder engagement within the UK national semiconductor industry and academia, but also internationally in order to understand what the needs of industry are now and in the near future, so that we can start doing the pre-standardization research and the discovery-led research to meet those needs. And I won't take you through all of that process, but just one slide to give you a sense of the priorities that have emerged. Now, these don't all apply to power electronics, but some of them at least do. So right at the top, this broad question of how you link nanoscale to wafer scale metrology. A lot of the research has started at the nanoscale, and we know that for compound semiconductors, the defectivity at the nanoscale is really important, but you want to manufacture at the wafer scale, and that's many orders of magnitude in terms of dimension that you need to straddle. And at the moment, metrology for that is inadequate. When you have novel device applications, you need to have new figures of merit. They need to be clearly defined. Many of the manufacturing processes need to have in-process monitoring, and again, those techniques don't necessarily exist. And hybrid metrology is the technique of using multiple measurements of different things, but how you can correlate them together to get more information out. Material defects, failure analysis, of course, important. Advanced packaging is a recurring theme where there's a lot of innovation happening, but some of it is very challenging in terms of the process development and the metrology. Device reliability and packaging, obviously really important to power electronics, and then emerging materials. So not just the new semiconductors that we're using, but the new dielectrics and processes for depositing conductors as well are important trends. Okay, so how can you actually get involved? Well, let me just give you a few things. Hopefully you'll be able to, everybody will be able to pick up something from this. So at a really basic level, I've said that standards is just any agreed way of doing things. So are you employing best practices in your research at the moment? So in your lab, have you got standardized measurement protocols, calibrations, uncertainty analysis? These are basic things. Often we take them for granted, but good to evaluate whether we're actually using those. But then also to link that to the wider community. So in certain fields, there have been quite concerted efforts for academics and RTOs, research technology organizations, to work together in defining protocols to make sure that results are comparable and to build consensus in a community at quite an early stage, so for university research rather than commercial technologies. There's also an opportunity to address some of these outstanding measurement and test topics. So that list I've just shown you, these are good topics where we understand quite well what the needs are. And so I would encourage particularly a focus on tackling these challenges, even at the very basic metrology and method development end. And there is a scheme, I'll show you a slide in a moment, called M4B, Measurement for Business. So if you're here from a UK business and you quite like the look of the capabilities that NPL might have for metrology, they can be made available to you at no cost to the company. You can get access to our capabilities and expertise if you're trying to develop new products. So that may be of interest to some. And then contributing to international activities. So there's an organization called VAMAS, and again, that's on the next slide, which is a voluntary international organization, so something that anybody can easily get involved with, which runs into laboratory comparisons. So quite a simple way of getting immediately involved in international standardization if you want to. And then, of course, the standard committees themselves. So as Alex mentioned, I chair the National Committee for Semiconductors, the BSI committee that feeds into IEC, and we're looking for members on particular topics. So the list at the bottom there, we need UK experts on mechanical and climatic test methods for semiconductor devices, on thermal standardization for packages, and also on electromagnetic emissions from integrated circuits. So if you're an expert on that, let me know, because we do have particular needs. But there are also the industry standards committees, so things like SEMI and JEDEC, which anybody can immediately get involved in. And so I'd encourage you to take a look at that if it's relevant to your work. Okay, so just one quick slide on VAMAS, which is a voluntary association that's existed for about 40 years now. In fact, it's having a 40th birthday this year. And this is a global organization, so it has representatives from all around the world. And it's essentially a community of researchers who are interested in standardizing and developing best practice for advanced materials. And we have just created, or about to create this year, a new technical working area on semiconductors. And so that feels particularly relevant. If you want to know more about that, do check out the website, but also just drop me an email. And secondly, just to share this scheme, M for B. So if you're here from a business and you want free access to NPL's capability, then look this up. It's a very simple application, and you can quite quickly get some free work done for you. I'm going to stop there and hand over to Vish. He's going to get more into the wide bandgap aspect, but of course, be very happy to take questions at the end.
Thanks very much, Seb. So I'm going to just spend a minute or two trying to get my screen shared. But whilst I do that, I should quickly... Oh, no, there we go. Right. Can someone let me know if they can see that, please?
Yeah, that's all good, Vish.
Thank you very much. So, thanks, Seb. And what I'll do is I'd like to take you through a case study. So, as Alex has mentioned, I'm with the power electronics team over at Warwick, and I'll introduce this a little bit more in depth now. But my remit has always been to develop the materials, to test the defects, to do fabrication, and to feed all of that back as a toolbox to device engineers and process engineers so that it can be fed into the application chain. So, like I say, I'm going to try and introduce Warwick, try and review silicon carbide wide bandgap materials. I'm not sure how many people on the call are materials-based or device-based. And one of the things that Seb has mentioned is an agreed way of doing things. I probably would even take that step forward of saying that standards, you know, it's almost a result of agreed communication style between people. I'll talk a bit more about that in a second. Then I'll cover defects. That is the particular case study that I'm going to bring forward in this presentation, where the standards for silicon carbide for defects have in the last 3 years just been made, and the thing is about standards is that they don't stand still. You can make a standard, and if new relevant technology comes up, you can update it as well. So again, I will start to bring into play, when did silicon carbide become a viable material, and when did other standards come in as well. And then we can talk about how those new things, when they come in, get introduced into standards as well. So I'm not sure if I need to do this, but I will spend a minute just quickly introducing REWIRE and its remit, because I think it's a nice story that goes into this standardization. So the whole point of REWIRE is that it's an innovation and knowledge center that works with companies in developing high voltage material and devices for the end application. And it's between 3 universities, Warwick, Cambridge, and Bristol. It's led by Bristol, but there are a number of different wide bandgap, so silicon carbide and gallium nitride, and ultra wide bandgap materials, aluminium gallium nitride, diamond gallium oxide, and boron nitride, that all feed into the process. So you have your high TRL level materials, which are actually in devices, and then you have your your materials which are really front runners to becoming the next new ultra wide bandgap technology. And the important part there is that if we're talking about the voltage rating, I always like to liken that to Moore's law. Moore's law for normal CMOS always wanted smaller and smaller, and it was a technology trend that you could follow, almost a standard by itself. But with voltage devices, it's similar but different. There are different voltages for different requirements, but you can see a technology trend as the voltage rating of those devices and those applications get higher and higher and higher. So something that's a domestic voltage supply is 240 volts. and something that's a medium voltage application like an electric vehicle is about maybe 1.2 kV. So the important thing is that current commercial devices, even for silicon and gallium nitride and silicon carbide, it can't fulfill the potential at the moment for these green applications. So it's a sorely needed technology. And as I've mentioned, we co-create all of our projects with industry as well. This is the other connecting thread between standardization and bringing new materials on board, because there is a discovery-led research that's happening here. And as Seb mentioned, the valley of depth between translation. The whole point of the IKC is to bridge those two things, and standardization, I think, is going to be one of those threads that pulls end application and discovery-led research together as well. This is obviously a UK initiative, but we have partners all around the world. And as you'll see in a couple of slides, the expansion of silicon carbide is a global phenomenon. So to quickly go through a fabrication line, for silicon carbide, the way that you make the wafers is different to silicon. In silicon, you'd have a vat of molten silicon, and you'd pull it from a crystal, and you could create, meters long ball of silicon and chop that up. Silicon carbide, you have to start from a powder. It sublimates, and then you've got to go and create the rest of your technology chain by taking that small puck. So you can get pucks which are maybe, you can see them here. That's maybe about 10 to 20 millimeters, that's centimeters high. Then that requires slicing, cutting, and it always needs to be said that if you're trying to cut silicon carbide with a silicon carbide impregnated tool, that tool may not last very long as well. But also that the damage to the device may also be quite, or the structural quality may be also quite damaging as well. But then what you'd like to do is then take your device, your layers, your substrates, which is over here, which has been sliced, and then perform epitaxy on them. You then want to take those, perform device fabrication, go on to do device and wafer dicing, package those devices, and then put them into the end application. Obviously, I am a materials person and a device person, so I will focus more on the first couple of steps, but it is not to say that the challenges for device packaging and applications is just lumped to two components. So they are a very wide and ranging field. But to introduce Warwick in this whole technology chain is that we're quite unique that we have an academic within the power group that represents each one of those components along the device fabrication chain. So Phil Morby started the group in 2002, and he brought all of the academics that you see on the screen to Warwick, and starting with myself, who does power materials, epitaxy, device characterization, fabrication as well, leads into work very well with Peter, Marina, and Ben as a kind of feedback circuit. But it is always really nice for me if I have a new discovery-led materials application or a characterization method to be able to go across the hall and talk to the guys who take the devices and blow them up and do device reliability tests. And they are both quite engaged with standardization themselves, talking about the electrical testing. And then they can even go down the line and talk to Li Ran, who does the end applications, or even Ji Hong and Ole, who concentrate on power control systems as well. So a quick review of the current silicon carbide field. And I will say that some of these slides, the images that I'm showing are from market analysts, and some of the most up-to-date slides there are from 2022. So there has been a small change in the market, or a large one, depending on how you look at it. However, what I'm trying to get across is where do the materials lie and how are they being developed? So as I've mentioned, the voltage for these devices is almost their class rating, and saying, what voltage are you developing that device for? Well, if you're developing it for a low end region, for something that's domestic, that plugs into your home, it will be about 200 volts or less. Something that's medium voltage, which may be EVs or uninterruptible power supplies or motors or PVs, is somewhere from the range of 1.2, even creeping up to 2.3. And then the high voltage regime, which REWIRE is really taking a lead on, is things like transportation. It's things like delivery of power. It's green energy renewable. And the important thing to note is that in 2022, they're thought to be a very clear delineation of where gallium nitride as a mature semiconductor and silicon carbide as a power, both as power semiconductors, had their roles. And it was this field here where it's the 600 to 900 volt, where both material types could find a niche alongside silicon, actually. But what I should mention is that with the recent developments that's been happening in both fields, I would say that gallium nitride is creeping up in voltage and silicon carbide might be creeping down in voltage as well. So the range of applicability is there. But to boil it all down, the device is really reliant on this epitaxial layer. This is the layer which withstands a voltage in the off state. And it is the layer where I will talk about the defects exist and they may start to affect device action. And this is just to say that silicon carbide has been a technology, a commercial technology since 2005, but it's been in applications, it's been in devices since 2013, with EVs being there. And currently the industry is worth about $3 billion US. With the previous growth of EVs, we were looking at a CAGR of about 25%, projecting about a value of 10 billion at 2030. That may be less now, but it shows the scale of growth that's possible. So, to analyze what's happening in that production chain, this is the year as we go and we progress, and each one of these components is where the costs of that end device lie. This is an analysis done by PGC Consultancy, but what you can see is that the top 3 squares of every single bar is either burn-in, epi yield, or die yield. These are things where, because the material is comparatively to silicon less clean or has more defects, there is an associated loss in terms of yield or loss of devices which has to be had so that the devices that come out of the factory are reliable. But what you can see is that those top 3 segments, as you go down, for whether it's for 150 millimeter wafers or 200 millimeter wafers, it could lead up to about anywhere from 20% to 30% of the overall device cost is just borne by the yield loss that's down the production chain as well. And it's important to note that why does it cost so much? Again, it's because when you create silicon, you can create a couple of meters of the material and slice it up, and then it becomes economies of scale. Very cheap to produce, very quick to produce. You could pull a ingot out of a melt in about a couple of hours. Whereas a silicon carbide boule is much smaller and can take weeks to make in concurrent manufacturing sense. So even though this figure here is from a paper from almost 2000s, the relative price index is actually pretty accurate right now. If a silicon wafer costs $20, I'd say probably about a month ago that an equivalent 6-inch wafer could cost $400. So more like a 20 times increase, but still very expensive comparatively. So the point of this is for standardization is, can we bring in measurement standards to try and either improve this epi yield or burn-in yield, or can we actually start to get rid of those earlier on in the manufacturing chain? Now, I've mentioned burn-in. The next slide will demonstrate exactly what burn-in is, but it's essentially stressing a device so that if it's going to fail, it fails early inside the manufacturer's facility and not in the end application. And it's not something that's really needed in silicon. What you can see on this right-hand side, these are 2 images from a technique called X-ray topography, which shows any kind of contrast or any defects as a part of contrast. I will go through the technique a bit more in detail later on, but what you can see is that silicon, it just looks like I've made a circle and I've just shaded it gray. It's because silicon is it is the purest and it is the cleanest material that we have been able to make. So there are very little defects in a normal silicon wafer. Whereas with silicon carbide, comparatively, even though it's still a high production technology, has a lot of defects in there. And the trick to silicon carbide is to classify those defects, determine what the end effect on the device is, and then to filter for those defects and improve the reduction of those defects down the line, which I will get into more in a second. Now, where does burn-in happen along this entire device fabrication chain? Generally, it's at the end when you've made the device, and you've had to go through a lot of steps to try and get to that point to actually figure out if that device is going to fail or not. And I should mention that there are two mechanisms. One is the gate interface and one is purely from defects. And these things are coupled sometimes. So if you have to go along this entire device chain, it can take a lot of effort and resource to get to that point. Whereas if we were able to filter for defects along this fabrication chain, then it could actually reduce the cost of the overall manufacturing as well. And this is just a quick slide to say, it's not to say that silicon doesn't need quality assurance and detection mechanisms. The thing is that it requires some kind of analysis as the devices are being made through the factory. But it's not the material going into the factory which is causing those defects. It is the manufacturing chain themselves and quality assurance at that point. So there are standards associated with silicon in that point, that way. I will skip through a couple of these next few slides because I'd like to get to the analysis side. This is just a slide to show what kind of timescale the silicon carbide wafers have developed over. So it's been almost 20 years since a 2-inch very defective wafer. And this isn't necessarily 100% accurate because still 200mm wafers are not on the open market. They may be used internally to some very large companies. However, they are still being produced right now, or still being developed right now. And this is to say, this is the spread of manufacturers who make silicon carbide wafers. And these are the ones that since 2018, there have been acquisitions and there have been companies that are looking to exit the market. But just to say that there is a spread across Europe, the US and China, which supply the wafers. And there is again a spread of some manufacturers which are vertically integrated, which use 6 and 8 inch. And there are some manufacturers that rely on external wafer supply. So the fact that standardization is needed is internal to that same company, but also so that when you're supplying wafers externally, you can be assured that the wafers you are buying are correct for purpose. I will avoid this from now. So I'll go through part of the standardization for defects in SiC. There is a zoo full of different defects. There is 0-dimensional, which is a point where an atom is out of the lattice. That's not really relevant for the technology at the moment. There is a 1D defect where it's a line, 2D where it's a sheet, and 3D where it's a gross defect inside the wafer. And the 3 defects that we should be taking away from this slide is the TSD, threading screw dislocation, the TED, threading edge dislocation, and the BPD. And it's an important one because silicon carbide is slightly cut off its crystal plane so that the BPD can expand across the entire area, but the TSD and TED are fairly vertical when it comes to that layer. So when you make your device, the TSDs and TEDs will definitely be interacting with the device, but the BPD takes time to get to the surface and interact. And why are they detrimental? When they reach the surface, they can create a nanopit, these TSDs and these TEDs and even the BPDs. And what that nanopit does is it increases leakage in those devices in the off state. So being able to actually analyze those defects and where they are and if it's a nanopit is quite important. And one of the important points is the dislocation density. That becomes our almost standardized metric that we want to know coming from these wafers. The other important point in silicon carbide is that a particular type of defect, the BPD, which is in the basal plane there, during device operation, if a lot of carriers get into that defect, they can recombine. And when they recombine, they can actually expand that one-dimensional defect into a two-dimensional defect, which becomes a killer. So it completely destroys the device action within your device. So to be able to control and detect BPDs has been quite a big exercise for the last 5 years. And then we have the three-dimensional defects, which are part of the technology limitation. They're not from the wafer themselves, but they will be really from the epitaxial process that you're performing as the next step to making the device. Technically, they all pretty much start at an interface or somewhere in the layer and then expand out to be these triangles. I will come back to these in a second. But what's happened over the last, say, 15 years has been a lot of discovery-led research into all the different types of defects, the zoo of defects in silicon carbide, how they form, what the best detection mechanism is, and what they do in a device as well. And what I'm showing on screen is not necessarily something that I want everyone just to, go through the detail of, but to take away the three different boxes. The red box down here is gross large defects, which will kill a device straight away. And these are things that you can control within a manufacturing house, but they are things that you need to be able to detect so that you can take chips out of a production process and not waste time in manufacturing them. There are then these blue ones, the basal plane dislocation, which can turn into the stacking fault, which need to be monitored because they can be a point of failure even if they are not a device killer. And then there's the green ones here, which are unavoidable within the device or the substrate themselves. And they essentially are 1D defects, and they can affect the device performance, which now that silicon carbide is a very high TRL level material and is a production device, there's a lot more interest in trying to detect these defects. But they being one-dimensional can actually cause problems in detection. And just to mention, this is a graph of amount of journals which have defect in the title or in the subject. And when did that interest start peaking? The introduction of 100mm wafers saw a very large rise of academic journals which mentioned defects. And as soon as another wave of wafer technology came up, or the size of technology, another wave of defect papers came up. Now, it's not to say that it's on detection or it's in reduction or it's in mechanisms, but just to say that every time a new wafer size comes up, renewed interest comes out. And as we can see, the 200mm wafer ramp is coming out, and we can see that there is actually a lot of interest in defects again. So defect detection methodologies. I'm going to pause on this slide because it's a wonderful paper that was written as a very top level, how do we detect defects? And I will go through it bit by bit now. These are all, I would say, fairly well-known techniques in semiconductors generally, but more at the lab-based level. To be able to turn that into an industrial technique, you have to start to agree on your standardization or how you start to measure these defects. You have to agree what type of defects you're actually looking for. But because it's over an entire wafer and there is a large defect density that you're trying to measure and control and compare, you then need to start to bring in defect capturing techniques, processing techniques, and analysis techniques. And all three of those of identification of defects, the technique, and processing then lead to a map of the zoo of defects on a wafer. Now, it's not to say that this is a typical device map, but it's not 100 miles off. And you can see the different classification of different defects, and I believe that this is probably by a photoluminescence method, but being able to characterize them and then put them into a defect density for comparison is going to be very useful, not only as you receive the wafers, but as a materials check as you go through that production chain of sawing up the ball, polishing the ball, making your epitaxial layer, doing implantation, which every single step can create defects. And this might be another slide that I pause on for a second. It's to say that there are different levels of defects in these materials, and silicon is way down here. It's a very low defectivity material, and it's very hard to find a single one-dimensional defect over an entire 200 millimeter or larger wafer. So you need to have a technique which is able to enlarge that defect and scan the entire wafer, which is not easy. But if you go up to silicon carbide, you can start to get a defect density which may be able to use either photoluminescence or X-ray topography, which is a standard which is just coming in or has come in. If you start to look at GaN, which is not the focus of this talk, but because you're having to put this on another substrate, it actually increases the defect density quite a lot. So you may be able to start to use some of these other techniques just at the lower end if you start to get into a very high quality GaN on silicon carbide. But what you most likely see in a lot of devices is actually you see GaN on silicon and you see GaN on silicon carbide, which is going to be a very high defect density, which means that you need to start to zoom into those defects so they don't overlap and just create a whole forest. And for those, you start to require electron microscopy techniques. Alex, how am I doing on time?
Probably got 3 or 4 more minutes just so we can have some time for Q&A at the end.
Okay. So I will quickly skip through the rest of these, but just to say that defect etching doesn't have a standard in silicon carbide because it's a destructive technique, and due to the expense of these substrates, no one wants to sacrifice those layers. Another standard which has just come in is X-ray topography, and that has come in both in the semi standards and in the JEDEC standards, and that's been translated to the IEC standards as well. And this is quite a nice technique where you shine X-rays onto a crystal plane. It acts like a disco ball, so you can look at lots of different images and they might tell you something about a different type of defect. And what's happened is that there have been 2 exposures, 2 different crystal planes that you can look at. The 0008 and the 11-28, where the 11-28 tells you about the basal plane dislocations and the other 2, the TSDs and TEDs, and the 008 only tells you about the TSDs. And it's required so that you can deconvolute what's going on. So I'm going to skip past these slides. Another big technique which has come in, which has not had tremendous amount of focus on standardization, is photoluminescence. That is where you put a laser light onto the semiconductor, it absorbs it because it's above the band gap, and then it re-emits light based on the type of defect that you have on the substrate. But what is really useful, and this is from KLA, is that you can actually perform other measurements whilst you're doing this photoluminescence, which is a light-based technique. You can look at the phase of the light, the slope, the spread of it, how the bright field and the dark field, to be able to determine other components of that. But then what is really needed there is, what are we looking at? How are we binning this? What signal are we using? And that's where standardization can really help with the photoluminescence method. And then I'll just skip on to the actual standards which have been coming out now for silicon carbide. And these have all just been published, where you have in the semi standard, you've got the guide to the amount of defects that you can find in silicon carbide. So now there is a agreed definition of those. There is now the other 2 requirements, so M91 and M93, which then determines how you use X-ray topography to go and characterize those defects as well. These have been kind of mirrored, but done separately in the IEC and the JEDEC standards, where we have one standard which defines defects, one which looks at PL, one looks at XRT, and one looks at homoprotectial layers as well. And then just to kind of plot this all on one graph so we can see it together, is that the wafer specs semi was published just before the 100 mil wafers came out. So that has been continually updated for these other wafers. The semi standard for the defect guide was published just before the 150 mil wafers, so that we can, that again has been updated. But the XRT, the measurement technique semi standard, has only recently come into play, where people can start to understand how to crosstalk on those characterizations as well. I will probably stop there, Alex.
Great, thanks very much, Vish, for that. I will just spotlight Seb once again. So yeah, really interesting. I hope that the those who are attending also found it as interesting as I did. If anybody does have any questions, feel free to pop them in the Q&A and I can relay them across to Seb and Vish. We don't have any currently, so I will start us off with probably quite a convoluted one around where the UK kind of sits on the global stage in terms of semiconductor standards. And then alongside that, where does sort of government, how does government interpret this? Like, do they see it as an area of priority going forwards to try and boost the sector's reputation, both nationally and internationally?
Yeah, let me have a stab at that. So does government recognise the importance of standards? Yes, absolutely. For critical technologies, that is understood. I think where it's less clear is specifically for semiconductors what the UK role is. So there are substantial initiatives within the UK looking at standards for like AI adoption, quantum technologies, engineering, biology, and so forth. In the case of semiconductors, historically, if you go back to the 80s, the UK was world leading in semiconductor technology. So technology developed in the UK was essentially being relayed directly into standards. That wouldn't really be the case now, certainly for silicon. The opportunity for the UK is in new technologies. So not trying to reinvent things that are already being done, not trying to get in the way of industry, which is happily standardizing its way through things, but to look to the future. So the technologies of 5 to 10 years from now, which are currently research efforts, if the UK is proactive in not just doing the research, but in standardizing it and building consensus, then we can, the door is wide open for us to exert leadership for emerging technologies and plant ourselves as the standard setters. I don't know, Vish, I mean, I guess you see it particularly for silicon carbide, whether you want to comment on that opportunity.
I mean, I think that it's horse-bolted gate stable, right? There's lots of fabs that have already been made for silicon carbide. There's lots of supply that's already been made, but I see lots of opportunities for standards to be brought in, because I know of instances where even within the same company on 2 different locations, their way of communication of what's going between them is still not standardized within the same company. But I would say that it's a learning platform, because we've got this new innovation of wide bandgap, which translates from silicon. So we can take the lessons learned from silicon to silicon carbide and apply that to the new materials which we are studying and developing within the IKC as well. So there's tons of opportunity.
Great. Are there any questions in the Q&A? So one on, are you aware of any developments on standardized methods for measuring dynamic on resistance in nitride electronic devices? That always seems to be an area where everyone argues about what the right measurement is. I am not aware of this. What has happened historically in the past, and I'll speak from a very general sense, is that probably 5 years ago, when you got a device data sheet, it was fairly bare.
device companies were still figuring out what their device could really do and in what circumstances. And obviously, they wanted to put their best foot forward. So I'm not 100% sure of any kind of standardization that's really happening in R-on, but I will put my hands up and say I'm not actively looking at that because I'm not a device person. So I would recommend, actually, if I can just plug my own guys at Warwick, is please do contact Jose Oryx Gonzalez and Lielities. I'm sure they will talk your ear off about that.
Yeah, I would add, I mean, I don't know the answer to that particularly, but there are 3 or 4 standards. I think there were 2 published in turn process on GAN device performance testing going through IEC. So do some Googling. But yeah, I don't know off the top of my head the answer.
One last quick one that has come in. So can standards help reduce risks in supply chains for critical minerals used in wide bandgap technologies? And is there a link to that?
100%. Yes. So, I mean, in broad brushstrokes, standards are the connective tissue for supply chains. So if there's a buyer and a seller, the standard is the thing that connects them together, the agreement of what they're shipping. And so standardizing the product improves resilience. And that's the general case. How you apply that to a specific mineral would be case by case.
Great. I think as we're already running a minute over, I will end things there. But yeah, just a massive thank you to the both of you, to Seb and to Vish, for those really interesting presentations. I'm just going to plug future webinars quickly before I sign everyone off. So we've got a couple more coming up over the next month. So one in July. I'm going to post some links into the chat for everyone. Please register on those. We've got one on focusing on net zero and sustainability, and a second one on scanning probe microscopy for sort of insights into electrical properties of wide bandgap semiconductors. So hopefully they'll be of interest to you as well. The registration links are in the chat. But yeah, just yeah, massive thank you again to Seb and Vish for those presentations, and a massive thank you to everyone for coming along today. So yeah, thank you very much.
Thanks, guys.
Thanks, folks. Bye.
Have a good day.